So, hi, I'm Toby. Thanks for coming. It's really great to be here. So, coroutines, what can't they do? What can they do? What are they? How do they work? Hopefully we'll make a little bit of progress answering, or at least maybe asking these questions. So, start with a little intro to set the context. So what am I going to be talking about? So there's lots of different things that get called coroutines. There's lots of things called coroutines in languages that aren't C++. There's lots of things called coroutines in C++, but I'm specifically talking about the technical specification called C++ extensions for coroutines, also known as N4680 to its friends currently. So I'll just refer to that as the TS from now on. There's a little link there. It's just there's a little screenshot of the front page, just to give you a flavour for how exciting it is inside. It's actually quite an easy read. It's quite short. It's quite nice. So, but what's the TS talking about? Well, apart from coroutines, it is an extension to C++. It includes 3 new keywords and some new customization points. So that's largely what I'll be talking about in this talk, how those keywords work, what the customization points are. And what it does is enables some new kinds of control flow, well, new to C++. So next bit's sort of, I'm going to run through how the transformation inside the compiler works, not in complete low-level detail, but sort of at a source transformation level. So first of all, what's a coroutine? So it is a generalization of a function. So coroutines are functions, but they're functions that have extra capabilities. So on the left there is a diagram that shows a caller calling a normal function. So when you call a function, control flow is transferred to the function runs to completion until it returns, and then control flow transfers back to the caller at the point where it called the function. So that should be pretty familiar to people who have called functions before. The interesting thing about that, well, I guess the boring thing about that, is that the function that's called runs to completion, and the caller waits for it and doesn't continue until the function's finished. So on the right, we have a coroutine. So in this particular case, the caller calls the coroutine, so that's the same as calling a function. But this shows off a couple of the extra capabilities of coroutines. So one is the coroutine can suspend, which transfers control flow back to its caller, and then the caller carries on, and then at some point later, the caller can initiate a resume of the coroutine, which transfers control flow back to the coroutine, and it resumes at the point where it was suspended. And then when the coroutine returns, it's just like a function returning. Control flow goes back to the calling function. So there's a couple of other interesting things that make coroutines different to functions, or at least more capable than functions. Than non-coroutine functions, I should say. So on the left there, we see pretty much the same thing as we had on the previous slide, but the first caller can actually return back to its caller without resuming the coroutine, and the coroutine stays alive. So the lifetime of a coroutine is not intimately tied to the lifetime of its caller like a regular function is. So then we can have some other function resume the coroutine sometime later, and that other function can be running on some other thread, for example. So there's an interesting control flow from the point of view of the coroutine that's possible there, where the coroutine can suspend on one thread and potentially resume on a different thread. And the other interesting control flow that coroutines have is they can be destroyed. So on the right there, we see one caller calls the coroutine suspends, the control flow transfers back to the caller, and then later on the coroutine can be destroyed, which transfers the flow of control right to the very end of the coroutine where the destructors and everything run. Everything gets cleaned up, and the bit in the middle of the coroutine is completely skipped, and that's quite useful, as we'll see a bit later on. So here's a really simple example of a coroutine. It's on the right hand side there. The coroutine. It's called Calculate. It's a coroutine that's so nice I wrote it twice. All it does is it performs some expensive calculation and then returns the result. So you can see there the first of the 3 new keywords, co-return. And the other interesting thing is the return type of this coroutine. So this lazy type is something that I've just invented out of whole cloth for this presentation. That is where a lot of the customization points sit. So this slide shows two different ways that this coroutine can be used. So the first one, the one on the top, is where the caller calls the coroutine but never uses the result. So in that case, you can see when this lazy result goes out of scope, the destructor of the coroutine is called, destroys the coroutine. The destructor of that lazy class destroys the coroutine, and the expensive work is not done in that case because no one wanted it. The second case, you can see the caller calls this .get, which resumes the coroutine, performs the expensive work, returns the result, and all is well. So this shows sort of an artist's impression, I guess, of what the compiler does to the coroutine body. So this is not exact. It's not specified like this in the TS, but this is kind of what the TS has an example like this. I didn't just make it up. So that on the left there is the coroutine body, just the same as on the previous slide, except slightly more colourful. And on the right is what the compiler kind of generates under the covers. So the first thing it does is it needs to find out the promise type. So that is the primary customization point for a coroutine. So it looks that up using this class template called coroutine traits. So it feeds into that as template parameters the return type of the coroutine and the types of any parameters. So there are no parameters in this case, which makes it easy. So that coroutine trait specialization needs to define a promise type. So then an object of that type is created. It looks like a local variable here, but it's actually stored in something called the coroutine state, which is a separate block of memory. So I'll describe that soon. So then the promise object, P here, that gets asked for the return object, which is what the caller of the coroutine will receive as the return value. And then the promise is given an opportunity to provide an initial suspend. So that allows the coroutine to suspend before executing any of the body. In the case of lazy, that's quite important because that's what allows it to not go and do the expensive work in the body of the coroutine until asked for. So I'll explain what co-await does shortly. So co-await is the second of the 3 new keywords. So then the body of the original body of the coroutine is executed. Co-return turns into a call to return value on the promise object. So the promise object can decide what happens with that value that's being returned. And then because we're returning from the coroutine, we skip over the rest of the body with that goto. There's no rest of the body in this case. If an exception is thrown, by the coroutine body, the promise object gets a chance to handle that in its unhandled exception member. And then at the end of the body is the final suspend point, so the promise again gets a chance to suspend the coroutine at the end of the body, which is not useful for lazy, but it can be useful for other things. And then after that is the point where a destroy of the coroutine will jump to. So the coroutine state is where the promise object copies of any parameters to the coroutine, any local variables that the coroutine uses, and also any information that is needed to identify where to resume the coroutine is stored. So this is some block of memory which is dynamically allocated. In a number of cases, and given a sufficiently smart compiler, that allocation can be elided, but in general there has to be a dynamic allocation, and the exact way that allocation happens is under the control of the promise object again, well, the promise type, sorry. So this coroutine state gets created when the coroutine's called and gets destroyed at the end when control flows off the end of the body. So that can be either when the coroutine is destroyed or when it finishes its final suspend. So co-await, that again expands into more kind of pseudocode. So on the left there, we've got a call to co-await. So X there is the thing that is being co-awaited, sometimes called an awaitable, but I have used the word awaitable to mean something subtly different in this talk, so there's confusion over that terminology. I apologize for that. So Y is what co-await returns. Well, it's the result of the co-await expression. So on the right there is what the compiler does for you. So this H is a coroutine handle, so I'll say more about coroutine handle soon. But that's what allows the promise and cooperating classes to control the coroutine. So first off, the promise object is given a chance to transform the awaited object. So if there's an await transform member in the promise type, then that gets past X there. That's optional, so that doesn't have to be there. If that's not there, then A just becomes X. So then there's this new operator called co-await. So if there's a operator co-await for whatever A is, then that gets called and the result of that is used. If there isn't one, then E just becomes A. So then we've got E, which is what I'm going to refer to as an awaitable. So that is another thing that allows you to customize the behavior of co-await. So that has three members. So the first is await ready, so that returns a bool, and that if that's true, then it means the coroutine will not suspend and it will immediately carry on. If it's false, then the coroutine is considered suspended, and when the coroutine is suspended, that means it can be resumed or destroyed. So if it is suspended, then await suspend is called, and that's past the coroutine handle. So that gets a chance to do something to the coroutine. It might want to stash that handle away, it might want to destroy the coroutine, it could even resume the coroutine. So after that, if the coroutine is still suspended, then control goes back to the caller. And then once the caller resumes the coroutine, control comes back here at that resume label, and then the coroutine is considered resumed. So then after all that's happened, the awaitable gets a chance to supply the result of the co-await expression via await resume. So co-yield is the third of the new keywords. And if you weren't looking carefully, you might not have seen anything change on the screen there. So it's pretty much exactly the same as co-await. Two differences. One is the first customization point that the promise gets crack at is called yield value instead of await transform. The other is it sits in a slightly different point in the grammar, so the precedence rules are different. But otherwise, it works exactly the same. So while we're going through these transformations, there's an extra one, extra bit of syntax called for co-await, which is just like a range for loop with a co-await stuck in it, and that gets transformed into the same thing as a range for loop, but with co-await stuck in it in a couple of places. So in particular, there's a co-await on the result of begin on the range, which means that can be could be an asynchronous operation or whatever the coroutine actually is, whatever co-await means in this context. And the other place is when iterating incrementing the iterator. So otherwise it works just like a range for loop, except the thing that's being ranged over is not a range as per normal. It's sort of an awaitable range. It's a different sort of concept where the begin on the range and the increment on the iterator has a slightly different type because it can be co-awaited. Well, it must be co-awaited. So I'll show an example of why this might be useful later. So coroutine handle I mentioned. So this is kind of like a non-owning pointer to the coroutine state. So it has its destructor doesn't do anything. That's the important thing to remember. And it has a default constructed state where it doesn't point at any coroutine. So there's an operator bool which tells you whether it is in the default constructed state or whether it's not. Provides a way of getting at the promise object, which is really useful. You can also go from the promise object to a corresponding coroutine handle. So these things can be not trivially, but easily copied. They're really cheap. They're just a pointer, basically. And the guts of what the coroutine handle is it allows you to resume or destroy the coroutine. So if you're dealing with one of these, you need to know whether the coroutine is currently suspended or not. If it is not suspended, then you must not call resume or destroy. There's not really any assistance for you in that regard. So yeah, this is kind of for dealing with coroutine handles. Writing the coroutine abstractions is kind of for people who are thinking very carefully. And it's fun to debug too. Okay, so quick word about return values. So coroutines transfer control back in more than one way. So there's the first time they transfer control back to their caller, and that's when they return the actual return value of the coroutine. The other way they transfer control back is when they suspend. So when the coroutine suspends, it will transfer control back either to the caller or the resumer. So there's just a minor difference in terminology. The caller is what's expecting the actual return value of the coroutine. A resumer is something that doesn't get any return value back. So the first time the coroutine returns or suspends, it goes to its caller and it returns a value. Subsequent times it goes to a resumer and doesn't return a value. Okay, so how do we actually implement this lazy kind of coroutine thing? So what we need to do is we need to implement a promise type, which I'm calling lazy promise, which are forward declared because the lazy class itself needs to refer to it, and it needs to refer to the lazy class. So first of all, we define the lazy class template itself. So start with its private stuff. So the constructor is private because it's only ever constructed by the promise object. So that's why the promise type is made a friend. There's other ways of handling that, but for exposition, I've done it that way. So when it's constructed, it gets passed a reference to the promise object, and it just converts it into a coroutine handle and stores that away. It also has an optional storing the value that's been computed. Starts out empty to indicate that we haven't computed the value yet. So then the public interface of lazy is basically just this get member. So what we do in there is we say if we haven't got the value yet, we'll go and calculate the value, and then we'll return the value. So in order to calculate the value, we resume the coroutine. So there's a little bit of an awkward interaction, which seems to often come up with this stuff, where we need to tell the promise where it should store the value once it's been calculated, because resume doesn't return anything. So there we're passing off the address of the optional that we're storing the value in off to the promise. And then we resume the coroutine. So that resume will return once the coroutine has finished executing. Then we null out our coroutine handle, which is important if you look at the destructor there. So in the destructor of lazy, if we still have a coroutine handle, if the coroutine handle still points at a coroutine, which means that nobody ever called get, then we can destroy the coroutine and skip over the expensive calculation. So the lazy promise on the right there, you can see it has a pointer to an optional, which gets set when the lazy is ready to receive the value that's calculated. So getReturn object returns one of these lazy objects, passing a reference to the promise. Initial suspend uses the special type which is part of the Coroutines TS called suspend always. So that's an awaitable type that always returns false from await ready. So that says we're going to suspend at the initial suspend point. So return value, so that's when the coroutine calls coreturn. Then we populate the optional with the value that was returned. Unhandled exception, we swallow and do nothing because I didn't write that part. So that, there's also, you should probably do something with the exception in that case. So final suspend, we use suspend never, which is another provided awaitable type, which just returns true from await ready. So we don't suspend at the final suspend point, which means that the coroutine will fall off the end and be cleaned up after it's returned. And then the final part of the puzzle is to specialize coroutine traits for coroutines that return any kind of lazy and take any arguments. And we just say the promise type is our lazy promise. Okay, so now I'm going to say a few things about the usual suspects for coroutines. So lazy sequences and async stuff. I'm not going to say a lot about these. I think there's probably better talks about that stuff at this very conference. So lazy sequences or generators, the coroutine is on the right here. So we've got something that returns a generator of int, which just gives you more or less infinite list of prime numbers. And the caller's on the left there. It just looks like a normal loop, and it is a normal loop. The nice thing there is that the coroutine doesn't need to care about the termination condition. That's taken care of in the caller. So the caller just stops calling it when it's had enough, and the coroutine won't deliver any more values if it's not asked for them. So async stuff. This is probably one of the big two killer features for coroutines, which I'm not saying much about in this talk. So let's say we wanted to have some sort of, I don't know, web service or something that tells us whether a number's prime, and we want that to be asynchronous because it could take a while. So on the right there, we've got a coroutine that does a couple of asynchronous operations, uses co-await to suspend if the value is not available immediately. So this return type task here is not completely invented out of whole cloth, but it's not part of the coroutine TS. It's something that you need to provide or find in a library. So then the caller gets this task object back, and then in order to get the value out of it, it needs to use co-await. So the caller needs to be a coroutine. In this particular case, you could have a return value that doesn't require the caller to be a coroutine, but things kind of line up more nicely if they are. So the nice thing about this is you can write your code. You can write normal loops and ifs and things as though everything was synchronous. Just sprinkle a co-await here and there, but it's actually asynchronous and will suspend the operation until the result's ready. So you can combine the two and have an async generator. So that's something that works just like a generator, but instead of using a range for loop over it, you can use a range for co-await loop. So if you want to use this stuff now, you can. So as far as I know, there are two working implementations of the TS. Visual Studio has had an implementation since 2015, I think. 2017 is recommended. You just need the /await flag. Clang 5.0 with libc++ has an implementation, which is pretty cool. So that just gets you the raw TS, which gives you coroutine handle and coroutine traits and a couple of other things. It doesn't really let you build, well, it lets you build everything, but it doesn't give you any high-level abstractions. So there's a few libraries that I know of that provide some of these abstractions. So one called CppCon, or Coro, I don't know. So that provides task, generator, async generator, some async mutex stuff, some other really cool stuff for dealing with async things. Highly recommend that. The Range v3 library has a generator implementation which works nicely with the Range v3 library. I am certain there are others, so if you're working on any or know of any that are awesome, please let me know. I'm always interested to find out about this stuff. So, I'm just going to say a couple of things about slightly unconventional things you can do with coroutines. So this is my personal interest my sub-interest in the coroutine space. So let's consider an example where we have some functions that return optional values. So say we're wanting to parse some values out of a stream. So we can read a word and it'll either return a string, which is the word, or an empty optional, which would be the case if there isn't a word in the stream. So similarly, we can parse an int. It either gives you an int if there is one, or if there isn't, it doesn't. And parse double, and then the interesting thing which we're going to implement is a combination of parse int and parse double, so called parse vector. So we're going to parse the count first, which is an int, and then that many doubles. And it either gives you a vector, or if the stream doesn't contain an int followed by that many doubles, then it will give you an empty optional. So this is kind of how I'd write that, not using anything fancy. So we call parse int, that gives us an optional back. We need to check if it's empty, and we can return empty. If it's not, then we can carry on, use that number, and then we just loop over that many times, call parse double, it gives us an optional, we check if it's empty. If it is empty, we return empty, otherwise we carry on to the next one. So it is possible to write this as a coroutine and remove a lot of the boilerplate code. So you'll notice the ifs have gone and all the early returns have gone, but this actually works the same way as the previous one. So we've put co-await in the places where we want to unwrap an optional, and inside that that can cause the coroutine to exit early and return an empty optional, or it can carry on. So how can this be possible? Well, strictly speaking, it's kind of not if you're talking about standard optional. My understanding is that it's not allowed to specialize a class template from the standard namespace without any user-defined types in it. But it works anyway, so it works. So we're specifying a promise type here called optional promise. So this optional promise, in its await transform, it says that you're allowed to await, well, if you await on any kind of optional, then we're going to return this special optional awaitable type, which is going to control suspension, etc. So the awaitable. So in await ready, if the optional that was co-awaited on has a value, then await ready returns true, which means the coroutine just carries on without suspending, and then goes to await resume, which just takes the value out of the optional. If the optional doesn't have a value, then we go into await suspend. We get given a handle to the coroutine, and then we just destroy the coroutine. And we tell the promise somehow that we're going to return an empty optional. That bit's a bit tricky. I haven't mentioned that here. There's code on GitHub if you want the gory details of how that works. But we destroy the coroutine, which means that we don't execute the rest of it. So what if optional is not quite enough information? Well, luckily, the exact same approach works if you've got something that's like optional. So, for example, if you had an expected class template, which could either be a value or some kind of error, you could use that. The implementation of the coroutine stuff for that is pretty much the same. So if you want to play with optional coroutines, there's I wouldn't say if you want to use it in production, but if you want to play with it, there's some stuff on my GitHub which works with standard optional, but only works on clan. Unfortunately, there's a basic expected implementation as well there. Just recently, the folly optional type from Facebook has grown support for coroutines, so that's not standard optional, but it's still pretty good optional. It's a good option, you could say. And the magic there is that works on Clang and MSVC, which is pretty clever. So there's also a folly expected, which doesn't yet have coroutine support. So that would be quite a good little project if someone wanted to play around with this stuff. I'm sure they'd appreciate a pull request. So the other potentially interesting idea, so this is something that I stole from Gore, is that you can get a kind of type erasure out of the coroutine machinery. So the interesting thing, well, I don't know, the thing is that the body of a coroutine can have more type information than the return type of the coroutine. So this is probably a bit hard to digest, this code, honestly. But what we've got a coroutine there. That create function there is a coroutine. So it's a static member function, which is cool. Coroutines can be static or non-static member functions. So this is a template also. So that template parameter f is more specific type information than is apparent in the return value of that coroutine. So that coroutine, its return type just encodes the return type and the arguments of the function, not the actual type of the function. And when that coroutine yields the function, the yield value member in the promise type on the right there gets called, and that can be a template. So that can recover the exact type of the function. So using this, you can build something that's kind of like std function, but just works completely differently. So one of the nice things about that is that if the compiler can see everything you're putting into this coroutine func thing, and it can see the caller, then it can potentially inline everything and get rid of all of the allocations and make all of the coroutine machinery go away. It's quite a cool thing to see. When I say the compiler, I mean Clang currently, but hopefully other compilers in the future as well. Otherwise, if the compiler can't see everything, it's going to have overhead. It's going to have dynamic allocation. It's going to have essentially virtual dispatch in there, so it's not going to be much different to std function. I think mostly this is interesting just as a sort of bit of a head scratcher and a that's interesting. What can we build? What can we build with that? So there's some code on my GitHub to play with. I wouldn't say it's useful as it is, but it's intriguing. So, in summary, coroutines are a generalization of functions. So that's a message that I think is important to bear in mind. Coroutines are functions. They're just functions that have extra capabilities. So the usual suspects for coroutines that we talked about: generators, async things, and async generators even. I think that's probably going to be the vast majority of uses of coroutines. But I think there's a lot of other interesting applications of coroutines that we're only just starting to explore. So there's the optional and expected case. I'm currently working on trying to extend that to other monadic operations. There's the type erasure example, which I'm sure has some interesting applications, and I really want to hear what they are. So thank you very much for your attention, and I'll be happy to take any questions. Yeah, go ahead.
Hi, as someone who programs in Haskell occasionally, my spidey sense tingled throughout the talk. It seems like coroutines are very similar or an extension of or a special case of monads. I was wondering if you could talk about that at all.
Yeah, sure. Yeah, that's along my line of thinking exactly. So coroutines themselves don't have a lot to do with monads, I think, but you can build something similar to Haskell's do notation, which is what I was thinking with the optional example there. So I don't think you can build the full generality of monads using coroutines. For example, the non-determinism monad requires going back and executing parts of the coroutine again, and that's simply not possible with the coroutines to TS. You can only move forward and can't go back in time. So unfortunately, we can't build everything that Haskell has, but it's certainly possible to build a really useful subset, and I'd love somebody to tell me what category theoretical subset that is.
Monads are the monoids in the category of endofunctors. Didn't you know that? I have no idea what that means.
Yeah, no, I thought they were burritos, but... Awesome.
Thank you.
Thanks. We'll alternate.
So when you spoke about the type erased callable, so you said like in principle if the compiler can see this much of the code, then it can optimize things away. It seems to me that that's pretty similar to saying like if on line 1 you assign a lambda to a std function and then on line 2 you call it, the compiler can optimize that out because it knows what that std function holds. So I guess I didn't really sort of get it. What are coroutines letting us do here that's unique, I guess? Because it seems like the situation is still pretty much the same. Like if you type erase, you might be able to get the optimization if the compiler can see enough code and sort of draw a line between them. And if not, then in general you won't. So what's different with coroutines? Not a lot.
Your observation is correct. There's nothing stopping the compiler doing the same optimizations for a std function.
It's just not as good at it with the function.
So, I mean, I'm not even claiming that there's really an advantage to the coroutine version. It's just interesting that capability exists within the coroutine system, and mostly I want to sort of prod people into thinking about what cool stuff they can build with that, because I'm sure there's something cool you can build there. I haven't figured it out. The function thing is just an example to show that it can work. Okay. I don't have a better answer. I'm sorry.
Okay.
Thanks. So I think we probably need to wrap up now. Well, I can take a couple more questions. Cool.
Hi. So on the slide, it was like 2 of n for implementing lazy.
Yes.
You made a comment about the you called it like a friction of having the promise and the value having like both know where the result is going to be. And I noticed that you put the storage in the return value and pass a pointer, the address of that, into the promise sort of after the fact. When I was playing with coroutines, my intuition was to do it the opposite way, and I was wondering if you could just elaborate why you did it that way, if there's pros and cons. Because I actually put the storage for the return value in the promise and just gave the return value knowledge of where that was.
So in that particular case, in that particular case, it's because I wanted to be able to destroy the coroutine, have the coroutine cleaned up while the lazy object itself was still alive. So if the coroutine runs off the end, the promise gets destroyed. So if the value is stored in the promise, it won't be available after the execution is finished. Now, it's possible to implement it such that the coroutine suspends at the end, and then the promise is available still. So that's a completely valid implementation choice as well.
I think that's actually what I ended up doing now that you describe it. And is there something that comes to mind as to what the advantages or disadvantages would be?
Well, the only advantage I can think of well, I think in the lazy case, there's not much advantage to keeping the coroutine state around. It's just kind of wasted memory.
Okay.
In more complicated cases, the promise has more responsibilities, and it would be a different trade-off.
Right. Okay. Thanks.
All right.
I have two concerns in highly threaded environments using coroutines. One, the coroutine state. There doesn't seem to be an allocator that can be passed into coroutines.
There is a customization point for allocation. If there's a operator new in the promise type, that gets used. So in terms of passing an allocator in, that is possible. The parameters to the coroutine get passed to the operator new, so it's possible to extract the allocator. It's a bit awkward, but it's possible.
My other concern is previously, on Windows, using fibers for coroutine style coding had a huge issue with thread local storage with the context switching. Is that still an issue with this coroutines library?
So I'm not sure what issue you were having. What was the issue?
There was an old bug in Windows where it would screw up the thread local storage using their fiber implementation. They fixed it with a compiler flag. There's a lot of old libraries that you could potentially pull in, or if they didn't compile it with that special flag, you'd still get screwed up thread local storage. I was wondering if that is an issue.
I'm not familiar with the issue, so I couldn't say if it is an issue with coroutines. Okay. Something to be aware of with thread local storage in a coroutine is that in some cases the coroutine might change threads in the middle. Everywhere it suspends, it could resume on a different thread. So thread local storage might not do what you expect. I don't know if that's related to the issue you're talking about or not.
Is there any thoughts of coroutine local storage in this proposal?
Right. Cool.
Is anyone thinking about adding coroutine local storage?
Not that I'm aware of.
Okay. All right, thank you.
All right. Okay. Thanks, everyone. Feel free to grab me around the conference and talk about this stuff. Thank you.